Welcome to the Explainer. Today, we are diving into the really cool mathematics behind robots that don't just follow orders, but actually, think on their feet. We're talking about systems that can learn, that can adapt, and that can truly master our wild, unpredictable world.
So, to get our heads around this, I want you to picture something. Imagine a high-tech facility over in Switzerland. There's a robotic arm, and it's handling these incredibly fragile vaccine vials. Now, it's dealing with tiny, tiny changes in weight, in temperature, even vibrations from other machines, stuff that would throw a normal robot completely off. But this one, it never misses a beat. It maintains perfect, absolute precision all by itself.
Now, that sounds an awful lot like magic, right? But it's not. It's actually one of the most elegant solutions in all of modern engineering. The answer has a name: adaptive control. And that is exactly what we are going to break down today. Okay, let's jump right in. To really get this, we first have to understand what makes a self-learning, adaptive robot so fundamentally different from a regular one. The difference really comes down to their whole philosophy. A traditional robot, it's built for a perfect, sterile, predictable lab. It has a fixed set of rules and expects the world to play along. An adaptive robot, though, well, it's designed for the real world. It fully expects uncertainty, and it's built from the ground up to learn from it and change its own behavior on the fly. So you might be asking, why do we even need this? I mean, why not just build better, more precise traditional robots? The simple answer is that the real world is messy. It's dynamic, it's always changing, and often in ways we just can't predict. And this messiness really boils down to four main problems. First, the robot itself changes. Parts wear down, lubricants get old, you get it. Second, the world around it is noisy. You've got vibrations, temperature swings, you name it. Third, the tasks themselves aren't perfectly uniform. Maybe one part is a millimeter wider than the last. And finally, and this is a big one, our mathematical models of the world are never perfect. They're always just simplifications. Your standard robot just can't cope with all that. So how in the world does it work? Let's pop the hood and take a look at the math that makes this all happen. But don't worry, we're not going to be doing any calculus here. We'll stick to some simple but really powerful analogies. First up is an idea called parameter estimation. The best way to think about this is that the robot is constantly taking its own pulse. It's running these very clever algorithms in the background to measure its own performance and update its internal map of itself and the world around it, all in real time. And that leads us to the heart of the matter, something called model reference adaptive control. Here's the idea. The robot has this perfect, idealized mathematical model of itself stored in its memory. It's like a ghost blueprint of its perfect self, and its entire job is to constantly chase that ghost. It compares what it's actually doing to what the perfect version would be doing, and it makes thousands of tiny adjustments every second to close that gap. Of course, a robot that's constantly rewriting its own rules, that sounds a little risky, doesn't it? I mean, how do we know it won't just learn the wrong thing and go completely haywire? Well, that's where a concept called Lyapunov stability comes in. Think of it as a mathematical safety net. It's a formal proof, a guarantee that ensures the system will always remain stable and safe, even while it's learning and adapting. Some of the most advanced systems take this a step further. They use a brilliant two-step process called self-tuning. So first, they use all that incoming data to get a crystal clear picture of their current state. And then, and this is the amazing part, they automatically redesign their own internal control software to be perfectly optimized for that exact situation, in that exact moment. It is literally like a mechanic rebuilding a car's engine while it's speeding down the highway. Now, this isn't just some theory locked away in a university lab. This technology is already out in the real world, and it's quietly revolutionizing some of our most critical industries. Let's start with aerospace, where performance and safety are absolutely everything. I mean, think about it. An airplane's physics change constantly as it burns through fuel and flies through different weather. This is the perfect job for adaptive control. A fantastic example is the Boeing 777X. Its advanced fly-by-wire system is using adaptive control to constantly adjust for everything: the changing weight of fuel, the shifting center of gravity, different atmospheric conditions, even how the wings themselves are flexing in flight. And the result? To the pilots, the plane feels perfectly consistent and incredibly stable, no matter what's happening outside. Okay, next up, semiconductor manufacturing. This is a world where precision is measured in nanometers, which is almost unimaginably small. And here,
adaptive control is unlocking a level of accuracy that people used to think was impossible.
Just look at this number. One chip-making plant brought in adaptive control for its wafer-handling robots, and they saw a 40% improvement in positioning accuracy. In an industry where a single nanometer can make or break a billion-dollar product, a 40% leap, well, that's not an improvement, that's a revolution.
And finally, let's turn to medicine. Surgical robots have to work in maybe the most unpredictable environment imaginable, the human body. This is a place where being able to adapt isn't just a nice feature, it is absolutely essential for patient safety.
Imagine a robotic catheter that has to navigate inside a patient's beating heart. It has to adapt in real time to that specific person's anatomy, to the rhythm of their breathing, the constant cycle of their heartbeat, and even the swirling effects of blood flow. Adaptive control is the technology that makes this kind of incredible, delicate surgery possible and, most importantly, safe.
Okay, so let's zoom out for a second. We've seen the how and the where, but let's talk about the big why. What's the real bottom line here? Why should a business invest in this kind of complex tech?
Well, the benefits are real, and you can count them. Companies are seeing massive jumps in precision, which means much higher quality products. They're seeing huge increases in uptime because the robots basically fix themselves and don't need to be taken offline for constant recalibration. And believe it or not, they even see big savings on their energy bills. But beyond those hard numbers, there is this immense strategic value. This tech gives companies a serious competitive advantage. It makes them way more agile so they can switch to making new products much, much faster. And it lowers their risk because it automatically handles problems that used to cause catastrophic failures. And honestly, this is just scratching the surface. The future is going to be all about fusing this incredible control theory with modern AI and machine learning. We're heading towards a world with not just single adaptive robots, but entire swarms of intelligent robots that learn from the world and cooperate with each other.
And that really leaves us with a final, very important question. We've seen how these amazing systems are learning to master the chaos of our world with stunning elegance. So the real challenge ahead is for us. How will our world, our industries, and our jobs, in turn, adapt to them?